In today's lesson, we're going to be solving for lengths of sides of right-angled triangles. Previous lesson, we had talked about defining sine and cos about the unit circle. If you missed that lesson, I'll link it in the top right-hand corner. So the result we had was that for a triangle having hypotenuse of 1 and measure theta, we discovered that the length of this side here, this leg of the triangle, was sine theta, and the length of this leg of the triangle was cos theta. And that was a great result. It also allowed us to solve right-angled triangles, but it only allowed us to solve right-angled triangles that have a hypotenuse of 1. What we want to do is we want to extend this triangle so that we can talk about how do you solve right-angled triangles that have an arbitrary hypotenuse. In this case, a hypotenuse of, let's say, r. So to figure out how to do that here, let's take a look here. We've got our angle here, theta. Again, this is about the unit circle, we'll assume, so the hypotenuse here is 1. By definition, this is going to be the sine of theta, and by definition, this will be the cos of theta. Now, I'm going to denote the hypotenuse of the larger triangle here. I think you guys can see here the bigger triangle on the outside here. I'm going to label that with the hypotenuse of r. And what we want to solve for is we want to solve for this length here, y, and then this length here, x. The way to solve this is to make the observation that the larger triangle on the outside and the smaller triangle on the inside are similar to one another. If you missed the lesson on similarity, I will link that in the top right-hand corner. But at any rate, we actually discussed this in that lesson, how this diagram here, this larger triangle and this smaller triangle are similar to one another. Because those triangles are similar to one another, I know the ratio of the corresponding sides are the same. So what I do know here is that the length of the larger triangle divided by the length of the smaller triangle, so y over sine theta, that must equal the length of the hypotenuse of the larger triangle divided by the length of the hypotenuse of the smaller triangle. Solving for y here, we get y equals r sine theta. Likewise, I can do this for solving for the value of x here. In this case here, the length of the leg of the larger triangle divided by the length of the leg of the smaller triangle must equal the length of the hypotenuse of the larger triangle divided by the length of the hypotenuse of the smaller triangle. And once again, we get x equals r cos theta. So this summarizes our results above. For a right-angled triangle, if that right-angled triangle has a hypotenuse of r, I know the length of this leg of the triangle will be r sine theta, and the length of this leg of the triangle will be r cos theta. So let's take a look at how we can use this result to solve right-angled triangles. All right, let's look at our first example here. So when you're given a triangle and you want to solve for a length here, in this case here, they want us to solve for this length here, x. What you do is you have to pick an angle that you're going to reference, you're going to work with. It's going to be one of your non-right angle angles here. So in this case here, I'm going to use the 35 degrees as an example. Now, we know that across from my 35-degree angle is your r sine theta. So by definition, my r value is my hypotenuse. So this will be 10 sine theta, but in this case, the theta is 35 degrees. So if I'm looking to solve for the length of the leg x, I know by definition, directly opposite is my r sine theta. So if this is r sine theta, I know that x equals 10 sine 35 degrees. If you punch in 10 sine 35 degrees on your calculator, you get approximately 5.74. Now, the reason I was saying that you pick the angle that you want to work with, we actually could have worked with this angle right here. It's not labeled, but I know that the sum of the interior angles of a triangle must add up to 180. So therefore, for this to add up to 180, this measure here must be 55 degrees. If I wanted to use this as my reference angle, we would have the following. Using the 55 degrees as my reference angle, now directly opposite this angle, this would be r sine theta, or 10 sine 55 this time. And this angle here would be my r cos theta, or 10 cos of 55 degrees. Therefore, x is equal to 10 cos 55 degrees, which is approximately 5.74, so the same value that we previously got. So you're going to get the same answer depending on what angle you choose. Just remember, directly opposite that angle is your r sine theta, and then adjacent to it is your r cos theta. Okay, let's take a look at the next example here. So I'm going to use the 40 as the reference angle. So again, directly opposite is r cos theta. Well, r cos theta, we know the length here is 15. It's given to us in the question, but I also know by definition this length is going to be r sine 40. So this will be x sine 40 degrees. So therefore we have 15 equals x sine of 40 degrees. I want to solve for x, so I'm going to divide across by the sine of 40 degrees, divide across by the sine of 40 degrees. These cancel. I get x equals 15 divided by the sine of 40 degrees. If you punch that in on your calculator, you'll get approximately 23.34. Okay, so for this question here, same idea. I'm choosing to use my 20-degree measure, but you could also use your 70-degree measure if you wanted to. But directly opposite, this is going to be my r sine theta, so this will be 15 sine of 20 degrees, which they don't ask us to find, but we can. And this length here will be 15 cos of 20 degrees. So now I know that x is equal to 15 cos of 20, 14.10. All right, same idea with this question here. I want to solve for this, so it's always best to label your triangle. I know I have my reference angle here of 30 degrees. Directly opposite is going to be 50 sine 30, and this length here is adjacent. It's going to be 50 cos 30. So in this case here, x equals 50 cos 30, which is approximately equal to 43.30. Continuing on here, again, let's use the 40 degrees. Directly opposite is going to be r sine of 40. And they want us to solve for x here. So if I'm going to solve for x, I know that x is equal to, in this case, 100 sine of 40, 64.28. Okay, let's take a look at this question here. It's a little bit different, so pay special attention to this question. Directly opposite, by definition, is going to be r sine 60. I don't know what the r is, so it's going to be r sine of 60 degrees. And adjacent here is going to be r cos of 60 degrees. Notice I can't solve for x directly. It turns out there's another trigonometric ratio that is studied. It is called the tan of theta. And the tan of theta is r sine theta over r cos theta, which a lot of times is simplified to just becoming sine theta over cos theta. So this is another trig ratio that you'll find on your calculator. And in this situation here, if I want to solve for the length x here, this is a situation where you're going to use your tan ratio. You can't solve it using sine or cos. We're going to solve it using our tan ratio. So the tan ratio says here it's going to be r sine 60 divided by r cos 60 is equal to tan of 60 degrees. So the tan of 60 degrees here is going to be r sine 60 over r cos 60, which is equal to x over 10. So therefore we have the tan of 60 degrees is x over 10. X equals 10 tan of 60 degrees, which is approximately 17.32. Okay, let's take a look at the next problem. Again, if I want to solve this here, I don't know what the hypotenuse is. I can label that with an r. Directly opposite this 42 degrees, by definition, this will be r sine of 42. And this length here, by definition, will be r cos of 42. So again, this is another situation where you're going to use your tan ratio. I want to solve for my variable x here. The only other measure I have is 7. Typically, you're going to use the tan ratio when you do not have the value of your hypotenuse and you're interested in the legs of the triangle. So in this case here, we've got the tan of 42 degrees equals r sine 42 over r cos 42, which in this case becomes 7 over x. So now we have the tan of 42 degrees is 7 over x. If I want to solve for x here, you always want to get your variable. The variable I'm interested in is in the denominator. I want to bring it to the top. I'm just going to multiply across by x. If you multiply across by x here, you get x tan 42 is 7. Again, keep in mind, the tan of 42 is just a number. It's just a number in itself, right? You can't divide across by tan or subtract 42 or something like that. This is all one expression, one value. So we're going to divide across by the tan of 42, divide across by the tan of 42. Those tans on the left-hand side will now cancel, and you will just be left with x equals 7 over the tan of 42 degrees, which is approximately equal to 7.7 7. Now I want to put that example off to the side. I want to show you guys another way you could have done it. Instead of using the 42 degrees, I could let this measure here be 48 degrees. So therefore, these lengths now will change. By definition, this length will now be r sine of 48 degrees, and this length here will be r cos of 48 degrees. So now, again, I still have to use my tan relation. So in this case here, the tan of 48 is going to be r sine theta, or r sine 48, which is x, over, right, r sine 48, which is x, divided by r cos 48, which is 7. So now algebra is a little bit easier in this situation. I just have to multiply across by 7, in which case we get x is 7 tan 48 degrees, which is approximately equal to, you guessed it, 7.77. So you're going to get the same answer using either technique here. Okay, there's an alternative method for solving for the lengths of sides of a right angle triangle. It's using the SOHCAHTOA method. I want to derive sort of how that works here. Again, just like the examples we had worked on here, you have a reference angle, in this case theta. As we know, directly opposite this angle, I'm going to label that with an O. This directly adjacent to this angle, I will label with an A, and always across from your 90-degree angle, you always label your hypotenuse H. Now, I'm just labeling the legs and the hypotenuse with this O, A, and H. Again, using this as my reference angle, I'm going to denote this as my opposite. This one as the adjacent angle, as it's adjacent to my angle theta. And then lastly, across from your 90 degrees is your hypotenuse. Now, by definition, we know that this is going to be H sine theta. And by definition, I know this length, we have denoted with an A, but it is also H cos theta. So what can we do with this here? You'll notice from here we have our opposite equals my H sine theta. So equating these two here, my O stood for my opposite. So I'm going to have my opposite, and H stood for my hypotenuse. And I multiply that by sine theta. So in this case here, your sine of theta is going to equal your opposite over your hypotenuse, which we can abbreviate as so. The sine of your angle is equal to your opposite over your hypotenuse. Likewise, I can equate these two values here, in which case we get my adjacent is going to equal my hypotenuse times the cos of theta. So now my cos of theta is going to be adjacent over hypotenuse, which we can abbreviate as ka. And notice here, the cos of your angle is going to equal adjacent over hypotenuse. And lastly, we have our tan of theta ratio, which tan of theta is going to be sine theta over cos theta, which is going to equal my opposite over my hypotenuse divided by my adjacent over my hypotenuse. The hypotenuses cancel here, and this becomes opposite over adjacent, which we abbreviate as TOA. And the TOA stands for the tan of your angle is your opposite over adjacent. So we can put this all together here. I've got the SO, the KA, and the TOA. So let's take a look at some examples of how you can solve right angle triangles using SOHCAHTOA. Okay, let's take a look at this example here. So again, you have your reference angle like we've always had. In this case here, I'll choose my reference angle to be the 65 degrees because it's already calculated for us. This is opposite my angle. Across from the 90 degrees is always my hypotenuse. The leftover one is always your adjacent. So in this case here, I want to solve for the x. I'm given the 25. This involves the O and the H. If it involves the O and the H, it's a sine question. So in this case here, the sine of 65 degrees is my opposite over my adjacent, and multiply across by 25, and you get x equals 25 sine 65. Let's try some more examples. Okay, let's try this example up here. So again, we're going to reference our 35 degree angle. I'll use that my reference. This is my opposite. Across from your 90 degrees is your hypotenuse, and the leftover one is your adjacent. So in this situation here, I want to solve for x, and they've given me the hypotenuse. So if you're looking at your SOHCAHTOA, I'm involving the O and the H, in which case it's going to be sine. So this will be the sine of 35 degrees is x over 10, and x is going to be 10 sine 35. I won't go ahead and calculate this because these are the exact same examples that we just did, but I am approaching this using the SOHCAHTOA method. Okay, let's try the next one. Same idea here. That's my reference angle. Directly opposite is going to be labeled opposite. Across from the 90 is your hypotenuse, and the leftovers your adjacent. This involves the O and the H again. So this is going to be a sine question once again because it's the So this is going to be the sine of 40 degrees equals opposite over adjacent. I want to go ahead and solve for x. So just like we did previously, you're going to have to still have to multiply across by x. And then that sine of 40 is just one number, so we're going to have to divide across by the sine of 40 on both sides. And I get x equals 15 over the sine of 40. And again, I'll leave it in this form here. We've already evaluated that number when we previously did it. Okay, let's try this one here. So again, there's my reference angle. Directly opposite, label that opposite. Across from the 90. Across from the 90 is my hypotenuse, and then the leftover is my adjacent. This involves what values? This involves the h and the x. If I'm involving the h and the a, I should say, this is going to be the ka, SOHCAHTOA. So this will be a cos question. So here we get the cos of 20 is going to be what? Well, it's going to equal my adjacent, which is x, over my hypotenuse, which is 15. Multiply across by 15, and we get x equals 15 cos 20. Okay, let's try this next one here. Again, grab your reference angle. This is my opposite. This is my hypotenuse. This is my adjacent. And in this case here, we're involving the A and the H. When you're involving the A and your H, remember, we're looking at SOHCAHTOA. And if I'm involving the A and the H, it's going to be cos again. So in this case here, we're going to get the cos of 30 degrees is my adjacent over my hypotenuse. So x is going to equal 50 cos 30. Okay, let's take a look at this example here. So for this one here, again, we've got our reference angle at 60 degrees, directly opposite. We label it opposite. Across from the 90-degree angle, we're going to label our hypotenuse, and the leftover is your adjacent. In this case here, we're involving, I want to find the x, and I'm given the 10. So that involves, if you notice, the O and the A. If that involves the O and the A, that's a TOA question. So in this case here, the tan of 60 degrees is going to be equal to what? It's going to be equal to my opposite, which is x, over my adjacent, which is 10. Multiply across by 10, and you get x equals 10 tan 60 degrees. All right, that concludes the example here. Again, you can solve this using the r sine theta, r cos theta method, or the SOHCAHTOA method. They're very, very similar, just a slight adjustment on them. Again, the idea behind the r sine theta and r cos theta is it connects with your unit circle in that definition, but you're free to use either method, whatever one you think is most appropriate. All right, thank you.